Right in front of us we have a Rosemount 1151 differential pressure transmitter here that we're going to be using as a level transmitter in this lab. This is a strictly analog only transmitter. It has no smart, no HART capabilities. It outputs a 4 to 20 milliamp signal. Over here on the right we have a Rosemount 3051 pressure transmitter. Does the same thing. It measures a differential pressure. It has a high and a low side, and it has HART capabilities, so it'll be labeled as a smart transmitter. We're going to be using these devices to measure infer the level in both a atmospheric tank here and a pressurized vessel that we have over here. You can see that it's enclosed and it's got a little pressure relief valve on the top there set for 10 psi. So we're going to be working with that. First thing we need to know is the relative density of the liquid we're going to be working with. And the liquid is in this tank right here. It's kind of bluish in color, but it's actually just water with a dye and some corrosion inhibitor as well. I think we have a label right here. Water, blue food coloring, and some a protector from, this is basically a corrosion inhibitor to help reduce corrosion. So what I've done is I've taken a sample of it and I've got it over here on the bench, and we've got a hygrometer here used for measuring, hydrometer used for measuring hygrometer is for humidity, hydrometer here for measuring the relative density. And you can see this goes from a range of just below 0.9 up to 1. And if I just bring in close, we want to look to the lowest part of the meniscus if we can see a meniscus on there. But yes, it looks like it's pretty well right at 1.000. So we can use that as our relative density measurement, a value of 1. So we just finished connecting our 1151 transmitter up here. This transmitter right down here, you can see I've ran wires from the positive and the negative terminals back over on this twisted pair cable back over to our 24-volt power supply right here. And I've hooked a fluke meter here. It's hooked in series with a loop and measuring a milliamp value here. I just lost it. I must have bumped something. Got a loose connection here. Yeah, I got a loose connection. So we'll fix that up. There, that'll work for now. So it's measuring 250 ohm resistor we were using, had that there just in case we wanted to connect to the smart transmitter. We don't really need that in this case, but so we're measuring a current. Meters hooked in series. What I'm going to go ahead and do is demonstrate 4 to 20 milliamp readings on some heights in our vessel over there, and have you guys calculate the hydrostatic head pressure for the lower range value and the upper range value for calibrating the transmitter in kPa. So let's go ahead and take those measurements. Calibrated up the 1151 transmitter here. You can see that I have the, let's see if it's labeled here. Yes, you can see the H and the L there. You can see that I have the white poly tubing here, plastic tubing, coming out of the H side, the high side of the transmitter, and it loops over and it's connected to the bottom of our vessel right here. I've got liquid in the vessel right now, and I've got a meter over here connected up to our transmitter. It's reading just over 20 milliamps. It was reading right on 20 milliamps, and we're at a level of about 64 and a half inches. And so I'm measuring right from the bottom of the cement here, and then we're going to compare that. We're going to take a measurement from our transmitter, center of our transmitter, to the floor. We're using kind of the floor as our benchmark. So 64 and a half inches, and it's reading, there you can see it's reading 20 milliamps right now on our fluke. It's sitting at 45 and a half inches down. I lowered the level down to the low range value, and if we look over here, you can see on our meter we're reading pretty close to 4 milliamps. So it's gonna be our lower range value for our measurement. And what we need to do now is measure from the center of our DP cell and subtract that off of both of our upper range and lower range value measurements, because it's going to be referenced from the center of the DP cell up to the liquid level right here and the upper range value. So we need to subtract those two. We'll need to subtract the measurement from the center of the DP cell off of these first two. Now I'm down here measuring. We want to measure from the center of the differential pressure cell. So about 32 inches from the floor, the center being right up here, kind of right in the center of that. I'll just maybe set the tape measure down here. So we want to be measuring right into the center here of this differential pressure cell. You can see that it's kind of got, the cell's got these two outer parts that are bolted on, and down in here is contains a diaphragm that senses the differential pressure. So I want to measure from the center of that up to our level here, and that's going to tell us how much hydrostatic head pressure. We would use that height measurement to calculate our hydrostatic head pressure for our lower range value. So we had that at 32
So now
inches.
what I've done, I've put a level in the tank, unknown level, and I've taken a current measurement here from the transmitter. What I want you to do now is to take, using the input-output formula, figure out what the height is in that tank. And just keep in mind that the lower range value is set. It's set at 3 inches in the tank. So we need to take that into consideration. That means that we need to add that. If we want to figure out the total height in our tank, we need to add that 3 inches onto the tank. And what I'll do is I'll just drain it off, and I'll kind of demonstrate that to you.
Just right here at 3 inches in the tank, this is where our transmitter is going to output 4 milliamps. So from that 10 milliamp reading, we need to be able to figure out what our height is in the tank. It's going to be somewhere in between 3 inches, and I'll just add the fluid up to the 20 milliamp value, so you can see kind of our range between 4 to 20 milliamps. We're going to have to figure out the value between there. So the value that we want to determine is from the total level in the tank from the bottom here. So there are upper range values at 22 inches in the tank. So from that we should be able to figure out what the level is of the unknown value, the unknown milliamp value that would be sent out to the control system.
This blue tank, we have a bubbler set up. You can see there, this stainless steel tubing runs down into our tank, and you can see the bubbles coming out of the bottom there. So that comes up out of these fittings down here, and the tubing runs down, and then it tees in. It comes down to our transmitter here on the high side. So you can see the high side right here of our transmitter. Low side just vented to atmosphere. If I go underneath here, you can see that teed connection. So this here is coming from our tank where the bubbles were leaving the tubing, and then this here runs up, and sorry, I had that backwards. This here is coming from the tank, and then this here runs up and over along this line here. We've got this little flow meter here, and they suggest about 1 standard cubic feet per minute of, well, that's per hour, sorry. So yeah, I barely have this cracked right now. We only want to have a couple bubbles coming out, and you can see down there, we don't have a crazy amount of bubbles coming, because what'll happen is if we turn this up, you can see our reading will start to bounce a lot more. Our pressure reading here. I'm gonna bring that back down just so we have a few more bubbles back to about what we were. And I guess the reading is still kind of bouncing, but not quite as bad, around 1.5. So, and then our instrument error is coming in from the bottom of this meter. There's a regulator, it's just kind of over there. You can see that gray regulator, it's got the tubing running out of it. That's supplying us our air pressure. So what'll happen now is we have that back pressure being created due to the hydrostatic head there of the fluid in the tank. So in this part of the lab, what I want to do is to take this pressure measurement. I might see if I can stabilize that. I'm just gonna close this off a little bit more. And there, yeah. There, I've got quite a few left. It's still bubbling, but at a lot lower rate. And you can see there, it's not quite bouncing around quite. We're right around, we'll take 1.50 kPa for our reading. What I want to do is take that 1.50 kPa and calculate how much fluid we have above that tubing, the end of that tubing down there. So by using our hydrostatic pressure formula, we should be able to figure that out, the height. So that's the last part of this lab. I use this gauge here, the transmitter over here. This is what would actually be measuring the device and outputting a 4 to 20 milliamp signal, but didn't have all the tools to get it set up and running. So this is kind of my quick
quick setup. What I did was I just ran this plastic line here and removed, there's a little vent plug here on the high side of the transmitter. So we're still measuring the pressure on the high side there. You can see this vent plug goes right in here where I made that connection. So this is the last part of the video where we've worked with, we've used a measured level on an atmospheric vessel, used a bubbler, and measured the relative density of a fluid so we can calculate our hydrostatic pressures of the fluids.